This is K8byp after Christmas working on the small broadcast tube tester. The tester is not what's small, it's the small tubes. The tubes suitable for amateur radio use will fit in this microwave oven cavity. But I built the tester enclosure, I built the power supplies, I built a mounting, chimney, all that stuff for the tube with an absolute guarantee that if I now plug it in, turn it on, and operate that tube, it will destroy the tube. Two reasons: excessive plate current. This is a 4-400 limited to 375 milliamps. I've got designed for 400. That's fairly easy to fix. But also there is way insufficient airflow, which will mean way insufficient cooling and overheating of the tube. Just for giggles, I've put a 15 CFM fan under that brown base plate. Well, that's the proper airflow. But see, the problem is it's only generating that at about 0.06 inches of water column, and a tube datasheet specify about 13, 14, 15 some CFM at 0.5 inches water column. And here's where a serious problem shows up, especially in amateur amplifiers. If we don't understand exactly what all these parameters mean and how they can lead to either a proper operating tube or one that's destroyed, has short life. And the absolutely the worst service for these tubes is amateur radio, because of oftentimes insufficient airflow, too much filament cycling on and off, mismatching, all that. So while this unit is not an RF amplifier, I'm going to use it for kind of an example and go through the factors that are important if you're building a new amplifier or if you've gotten an old one and it needs to be reconditioned. Here are the gotchas. Here are the things to look out for that can lead to either the tube being destroyed or not. Number 1 and 2. Easiest ways to destroy these tubes: incorrect filament voltage and current. They're specified by voltage. The 4-400 specified at 5.0, give or take a quarter of a volt. It is absolutely mandatory to measure that at the base pins. See, I've got the filament pins sticking out just a bit so I can reach in and measure them. Absolutely mandatory to measure at not only at the socket but on the pin to detect a bad socket. First thing to do if you get an old amplifier, change the socket. It's guaranteed that the socket terminals are oxidized or corroded. But just in this test setup with this 16 gauge filament wire from the filament supply through a 0.01 ohm dropping resistor to measure the current, and out to that socket there's half a volt drop. So when I set the power supply to 5.0 volts, that filament is out of range automatically, just because of mostly the drop across that wiring. So absolutely mandatory to measure at the socket. Now, of course, that's dangerous. That can be hazardous to do unless the other voltages are turned off. At a minimum, just supply the filament and measure it without the high voltages. But the most proper thing to do is actually connect two small gauge wires to the filament terminals, bring them out, so that can be measured remotely. Do that through a couple RF chokes that can be left in as a permanent modification. The other big way to destroy these tubes is filament cycling. Turn them on and off once a day, twice a day, you're going to destroy the tube. These are not amateur radio tubes, they're not hobby tubes. They're industrial, they're broadcast, they're scientific. They're intended for use in radio stations where the thing is turned on and it's left on for 3 months, 6 months, a year, and never turned off unless there's maintenance required, a tube fails, or there's a power failure. That off and on causes severe mechanical stress to the filament assembly and also the cathode. And even if the filament voltage is correct at the socket, when the tube is cold and turned on, there tends to be high current, but also a time when it's warming up that the filament voltage is naturally low. And depending on the cathode material, Operating at low filament voltages can destroy the cathode. It's called cathode poisoning. And W8JI says that's much worse with high plate voltages, so that makes a case, especially in amateur service, to use lower plate voltages. For this tube, the lowest distortion case on a datasheet is at a plate of 1500 volts. There's no need for amateurs to run 3 or 4 kV on these tubes. Complete waste. And do not believe for a minute that just because the amplifier has a step start, or someone heard of the concept of step start and guessed at how to make it, that it is correct. My recommendation is to monitor the filament current and bring the filament up with a variable power supply or a variac and keep the current below the operating current, which for this tube, this is a 4400 with a reduced filament power cathode. It only takes about half the filament power for this tube, so I'm reading about 7 amp instead of 14. But a safe bet is to keep the startup current at all times below that figure. It's also very bad to turn it on quickly. It's also bad to turn it on and immediately start operating the tube. These things take time to warm up. Incidentally, just turning the filament on and setting it at 5.0, I measured with only marginal airflow. I measured 170 degrees Fahrenheit at the top of that glass envelope in that tube. Realize that adds to the operating heat when a tube is amplifying. Number 3, insufficient airflow, and that's where this tube in this test unit would be destroyed. Just for giggles, I put in a small 15 CFM 0.05 inch water column fan, knowing it was too small, but something's better than nothing, just for prototyping. And I measured 0.06 inches water column with the fancy digital manometer, because airflow is difficult to measure. The datasheet for this tube says 15 CFM at about half an inch water column, 0.5, not 0.05. Well, what's the difference? Airflow is airflow, right? That is wrong. Airflow in cubic feet per minute is the outer dimensions of a box that can contain that much air. What is required here, and why they specify CFM at pressure, is that what's required is what in the automotive world is known as mass airflow. Just like a 1 cubic foot box at 70 degrees contains less air than that same box at 0 degrees because the air is denser, the same applies here. There is more cooling air plus flow. Let's assume the flow is the same. There's more cooling air going past the tube to pick up more heat at half an inch water column pressure than there is at this fan at 0.05. Just for a crude assumption, I'm going to assume there's 1/10 of the airflow necessary. And I knew it wasn't right because when I turned the fan on after warming the tube up, the temperature didn't go down quickly. It just kind of slowly dropped down. And very little air coming out of the top of the chimney. And by the way, that's an iMac chimney. Do not operate these tubes without this correct chimney to direct the airflow. And lots of amateurs make that mistake of not using a chimney. That chimney's there to curve that airflow across the top of that glass envelope and up to the seal, that dark area below the silver. And without the chimney, that seal may overheat and break. So it is absolutely mandatory not only to supply enough airflow, but to supply it through these little holes in the base of the tube. The smallest holes are where the pins go through this board. The larger holes and the large center hole are where the air go through, up through the base of the tube, where the leads come out, up through the chimney and up to the plate. The area, if the tube is on top of this plate, if we're looking under the chassis at the tube with a pin sticking through, there must be an enclosure under here to direct and concentrate that airflow into those holes. It is not sufficient to just have this sitting on a chassis and to attempt to pressurize like they did in the old days, this entire chassis area under here. That takes a huge blower, because the pressure, which is implied by the 0.5-inch water column figure, that pressure is divided along the surface area of that enclosure in there. And if we try to blow down the entire enclosure, there's going to be weak airflow through those holes. Pressure is a function of area. So it's necessary to put a fan or ducting from a fan or a blower concentrated around these holes. There's a small enclosure under here where the plate tube terminal of the magnetron entered. This is a microwave cavity underneath. It's a little smaller in dimension than that. It's about this size. So if I direct the airflow into that cavity, then that will force the airflow through those holes at a higher, what's called static pressure. That's referred to as the static pressure, 1/2 inch water column. So for example, a fan mounted like this cannot possibly create enough flow and pressure to guarantee the correct air density for correct cooling. Because again, this 15 CFM is a flow parameter, and this relates to the air density. And the more dense the air, the more air molecules there are flowing between the chimney and the tube, the more cooling there will be. Number 4, input matching. Generally we use either Class A or Class B or some version in between for RF amplifiers. In the amateur service, we avoid Class C because it's very dirty, lots of harmonics. When we discuss Class A and B, we usually look at the plate, but that's a starting point for dissipation and setting up voltages and bias and all that. When it comes to the exciter driving the tube, there is a serious problem in Class B that does not exist in Class A. In Class A, if this is a waveform of the grid drive, and the dashed line is the zero with reference to the input signal swing, and the solid line down below is cut off of the tube. In Class A, every moment of that driving signal is changing the conduction of the tube. That means the exciter is always looking into the input of the amplifier and always working. In Class B, we tend to run the grid at cutoff, which effectively moves the driving waveform down to half cycle. Since Class B, in theory, is half cycle on a plate, that means that the grid cathode bias from that driving waveform is also half cycle. And the grid to cathode space, just like a transistor base to emitter, is a diode. And there are extremely few old references that discuss this. It's very obscure. But what this means, when the exciter is looking into the tube cutoff, and half the exciter wave is operating and half is cut off, that means that the half that is cut off is more or less looking into an open circuit, and there will be a high SWR. All that energy, or much of it, is reflected back to the exciter. And since SWR meters take a long time average, they will not detect this. And this is a source, in a Class B amplifier especially, of why the exciter is seeing an SWR. And then in vain, designers and hams tend to try to throw tuned circuits and matching at it, and it doesn't solve anything. An example of that is this classical arrangement of the RF exciter drive coming in at the left and a negative grid bias V sub G minus coming through a parallel tank. And hams have invented some myth that tank does some kind of matching, and that is wrong. The purpose of that tank is to be parallel resonant at the frequency of the exciter so that it is an open circuit to RF, and that isolates the RF from the grid source, because the grid source is from a power supply which is filtered and bypassed. And if that tank is not there, or if it's not tuned to parallel resonance, or it's not efficient, then the RF signal will be shunted to the grid voltage supply and shunted to ground. So it is a myth that that network is there for tuning or matching. In the 4-400 at certain conditions, correction, the 3-400 grounded grid, under certain conditions, the grid input is 120 ohms resistive. That's a serious mismatch to a 50 ohm transmitter. So that implies that looking into the grid, apparent conduction, this is the exciter seeing a 120 ohm load. And it's no big deal to match that. But down here on a negative half, the tube's open. There's maybe a 5 picofarad parasitic capacitance, but that's not a load. So the input matching problem, and a tuner will not fix it, becomes a significant problem, because that if the transmitter sees, especially a solid state exciter, sees a reflected power, it's going to scale back the output. And no fake tuner, no matching network by itself can fix that problem. Parasitics. W8JI correctly says that some people claim that the parasitic oscillation destroys tubes, and W8JI says that's wrong, and he's correct. Parasitic means the tube simply oscillates at full tilt, full power. That process is limited by the power supplies and by the emissivity of the cathode, so it's a limited process. What parasitic oscillation will do will immediately take the tube to full maximum drive and output, regardless of what the exciter does. And if the tube is properly set up, properly biased, has proper cooling, it's not going to hurt anything. Because 400 watts plate dissipation is 400 watts, doesn't matter how it happens. A broadcast engineer told me that he built an amplifier and it had a bad parasitic and it went into oscillation. He said the plate turned instantly white. He had to dive for the power switch, but he said it didn't hurt the tube at all. So parasitics are a problem. Parasitics are a matter mainly of the screen grid connection. Parasitics, if you're designing or building an amplifier, need to be tested for by simulation, by signal generators and such, before ever throwing power to the tube. That gets to be complicated. In an old amplifier unit, old bad connections, electrical, especially on the filament, will destroy a tube. There's a lot of myth around the idea that old tubes are gassy, therefore they arc. Yes, that happens. But in this tube, if what I read is correct, that plate is a getter. Basically, what it takes is just warming it up and operating it for a while to get the gases out. The big gotcha for plate arcing, and I saw it happen in a Drake TR3, and there's a video here on a Drake where I explain this, is that the load capacitor, of the plate and load controls. That load capacitor these are both air variables, but this one had a bad ground on the rotor, and when it was set to 20 meters with the pointer about straight up, there was a dead spot where that ground contact was badly worn and eroded away, and that capacitor broke contact, and that capacitor went open. And back in here is the tall, what's improperly called a plate choke. It isn't, but it's that tall coil there. I sit and watched that coil explode. It went pop, 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 and 5 fireballs and 5 turns of that coil vaporized. And if you'll read W8JI's information on this, he explains this about improper load conditions or bad connections or load faults that can cause the plate voltages to be bigly multiplied. And in that TR3, that tube is good for 6,800 volts maximum plus. And since it arced over from that coil to the plate control stator, and that was about 3/4 inch, I would approximate that voltage because of that load capacitor opening reached maybe 4 to 6 kV. Excessive plate voltage will definitely cause arcing in these tubes and destroy them, whether they're gassy or not. So these are the factors that give hams fits, even broadcast engineers. But to sum them up, guarantee all the other power supplies off, guarantee correct filament voltage, current, and startup time, and warm the thing up 5 or 10 minutes. Don't be in a big hurry. Airflow has to be measured. We cannot put in a fan that's 15 CFM at a half-inch water column and assume that's good enough. As the fan ages, airflow is going to be reduced. Does the fan have enough overhead to compensate for it? Input matching. Load it where it should be, not enough drive, especially with a solid-state exciter with a computer control that senses SWR and decreases power. That's probably why. It's this Class B high SWR problem, assuming your amplifier is Class B. Parasitics, test them by driving a 50 ohm generator into the antenna jack and adjusting, changing things with the tube off. See if you can find any sweep frequency, see if you can find any resonances. Parasitic in the Drake TR3 was, there was a response at 20.8 megahertz and one at about 183. Strange frequencies. And if you've got an older amplifier unit, it is mandatory to tear it down to nothing, put in a new socket, either disassemble and repair the ground on a load capacitor, make a new ground for it like I did in the Drake, or replace the load capacitor. You may spend about as much as a tube for that capacitor, but if the capacitor is old and bad and fails and destroys the tube, then you're going to be paying twice as much. But all the electrical switch relay connections have to be scrutinized, cleaned, polished, deoxidized, or replaced, or you'll have nothing but trouble. And especially with drive problems and insufficient plate supply. Overdriving and insufficient plate supply leads to splattering, and that's a violation of FCC regulations. And that causes serious problems, especially when propagation is in short. And people are violating FCC rules by using amplifiers to talk locally. Splattering shows up and causes quite a bit of problem. So in no case can we ever just buy another tube and plug it in an amplifier. Read IMAX datasheet. Each tube must be set up individually. We can't just take one out and put a different one in without at a minimum checking for the filament conditions. So the envelope, the chimney, all that should be the same. Airflow should be the same. But with these tubes being somewhat scarce and expensive, it pays to pay attention to these details. K8byp did it.